Hello and good morning. My name is Molly Tucholsky, and I'm a student assistant here at the lab. Welcome back to our Summer STEM Career Talk series. Berkeley Lab is a Department of Energy research facility innovating in materials, life sciences, energy, and more. Today's STEM Career Talk will be moderated by our two experiences in research interns, Kyla and Dominique. If you want to see previous talks, please check them out on our website. The link will be in the chat below. Passing it off to Kyla and Dominique now.
Hello everyone, my name is Kyla and I'm an intern here at Berkeley Lab over the summer in the Experiences in Research program, and today we are joined by some amazing panelists to talk about microelectronics.
Good morning, everyone. My name is Dominique, and I am also an Experiences and Research intern here at the lab. Kyla and I will be hosting today's career talk, and we are very excited for this panel. For those who don't know, microelectronics is defined as the design and fabrication of extremely small electronic circuits. These components, often at the micrometer scale or smaller, are essential to computers, phones, medical devices, and more.
Okay, so I'd like to start off by introducing our panelists for today. So first we have Dr. Revati Jambunathan, who is a research scientist in the Center for Computational Sciences and Engineering in the Computing Sciences area here at LBNL. So now we'll be turning it to Dr. Revati to give a quick introduction of herself, her work, and a brief explanation on what microelectronics is.
Good morning. It's great to be here. Of course, I'm meeting you all virtually, but I'm really excited to talk about microelectronics with you. And I want to thank Faith and the interns and Kalila, Molly, Dominique for putting this all together and then for inviting me. And also, it's great to be along with Andy, Fiero, and Jared on this panel with them. So it's an honor. All right, so I am Reva, and as Kalina mentioned, I am a research scientist at the Applied Math and Computational Research Division at Lawrence Berkeley National. So let me give you, I have prepared this really short presentation that talks a little bit about my journey and then talks a little bit about microelectronics. And hopefully it introduces you to the vast realm and the spectrum of microelectronics, right from atoms to architectures. All right, can someone confirm that you can see my screen? Yes, okay. So this is just a picture of fabrication of these microelectronics integrated circuits. And I'll be talking a little bit more about that in just a few minutes. But where am I from? I grew up in this place called Pune, India, in India. And it's about 3 hours drive from Mumbai, if you know, that's a popular city and people generally know where Mumbai is. When I was in high school, when I was in middle and high school, I used to play field hockey, and that's my field hockey team. And what happened was when I was in 8th grade, which is, you know, the beginning of high school, our hockey coach took us to a place for camping. It's called Panchet. It's about just an hour and a half away from where I lived. And they had arranged for an astro night session. And so there we were, dark, starry skies. And and the first thought that came to my mind was, oh, this space is really cool. I want to do, when I, I want to have a career in astrophysics and do something related to aerospace and things like that. So that's what sparked my initial interest in science and in aerospace engineering. Then I did my undergrad in aerospace engineering from the southern part of India. And then I did my master's from University of Illinois and also PhD from University of Illinois Urbana-Champaign in aerospace engineering. And so you can see that, you know, that's a 1 day plus 1 hour journey to go from where I live to, but it's not door to door. And then once I finished my PhD, I joined Lawrence Berkeley National Lab as a postdoc. And if you ask me what I'm doing today, I'm taking the skills that I learned from my throughout my education, from my PhD, and apply it to different applications that are of relevance to the Department of Energy and also to all of us in general. So one of them is microelectronics. So applying what the skills that I've learned, the math skills, the computational skills, and applying it to problems that are of interest to us. So microelectronics. As Kalila already mentioned, these are really micron scale chips. Actually, at this moment, they're nanometer sized. And they are ubiquitous. They're there everywhere. They're there in your phones, in your pocket, in your wrists, to the laptop that you use. And they are essential, and they have a large impact on healthcare, on climate change and security, and things like that. And all this is possible because over time, these integrated circuits and chips have undergone a ton of miniaturization. So let me go back to 1945. This is called an electronic numerical integrated computer, ENIAC. And we required an entire building to store that computer. And now you have something that is a billion times more powerful than that first computer, and it fits on our palm, it fits in your pocket. And that is the power of miniaturization. This has happened due to something called as Moore's law. Moore's law is where they say that, it's known that every 2 years, the transistors that are there on the chips become 2 times smaller, or you can fit double the number of transistors on that same area. What that means is that we can have, let's say you have a chip size, a given chip size. In the next 2 years, you can have double the number of transistors on it. And so with time, it's become more and more powerful, and the transistors have become smaller and smaller and smaller. And now it's almost the size of a nanometer, which is, a few angstroms or a few atoms. And we are at the cusp of 2 different phases, and I'll talk about both. One is the need for advanced manufacturing. Because if you have to manufacture something that is really tiny, that is of a few angstrom size, or or the size of a few atoms, you have to be really, really precise. And that is our current challenge when it comes to manufacturing. And so there is actually a very nice video on YouTube that talks about fabrication. And I'll ask somebody to post it. I'll find it and I'll post it on our chat before the end of this session. But here is just a pictorial overview. So you initially start off with something, like sand, and you take that sand, convert it to silica or silicon, and that's our substrate here. And then what the next thing that you do is apply this masking layer, and that masking layer is then exposed to UV light to create a photoresist. Now you have that photoresist will remove this, the UV exposure will remove this yellow layer. And so now you have this sandwich structure with the substrate, the masking layer, and then the photoresist. And our next goal is basically to remove the region that's below here. And that's what we're doing here. So now you can see that we remove this photoresist, but we also remove this portion, and that's called etching. So when we mask and apply the photoresist, we do it, and that's called patterning. It happens to something called as lithography. And that patterning process decides what is the shape or what is the pattern for that integrated circuit. Once you have that pattern, then we remove those regions through a process called etching. Etching basically means removing the process. And the thing that I will focus on next is this etching process, because that requires, imagine the size of this width is just a few nanometers, or a few bits of your hair strand. And so that's how precise we need to be when we are etching these devices, etching these substrates. And so what I do is, and Andy here is my collaborator on the panel as well, and both of us work together on this project, where what I'm showing here is a reactor. It's actually the machine inside which that etching occurs. So what happens in here is the gas is introduced, it ionizes. Ionizes means that we strip off some of the electrons, and now you have positively charged particles, negatively charged particles. The positively charged particles, let's say the red ones, move down towards the substrate and start removing that blue portion that was patterned out. And we model that. And we try to understand the process by which we can do this more efficiently and help our experimentalists to then set up the experiments and really see whether what we see in our simulations helps them and guides them run optimum parameter configurations for their fabrication process. And so there are a lot of complex reactions that occur near the surface, and we try to capture all of that, and that is our current computational challenge. And I'm happy to talk a little bit more about this if you have any questions after, but I just wanted to give you a broad overview of the fabrication process, what we do as computational scientists, and what we like to focus on when it comes to manufacturing. I mentioned to you earlier that there are two forks that I'd like to talk about. One is the fabrication process, because that's one of the challenges that we face right now because of the miniaturization of these chips. The second one is, as there's something called as, we're reaching the end, or we're beyond Moore's law, where you cannot get smaller than the size of the current chips, or, well, you can, but then it gets harder and harder. And so we are now at the cusp of developing new materials and new energy efficient microelectronic devices that explore other properties of materials to develop a completely new microelectronics chip. And so, and these can range from, spintronics devices to quantum chips to electric components. And the challenge here is we don't quite understand how these new materials are going to behave in an integrated circuit. And so what we do is we take a co-design approach where we go from the materials and then go up to putting it in an integrated circuit. And we go back and forth to understand how material affects the circuit, and the circuit then also drives the material discovery. So that's an entire co-design process. And this is another aspect of microelectronics that I wanted to share with everyone. So just a few things to think about is this is a really exciting field, and there's a lot of innovation happening right now. And it's a great place to explore a career path. So what do we need? We need people with curious minds, ask questions. There are many career paths here in the science, engineering, programming, and others beyond science, engineering, and programming. I hope you take advantage of internship opportunities in this, and I'm also happy to talk about other things as well. Thank you. If you have any questions, we are happy to take them.
Yes, thank you so much, Riva, for giving us more background on both your journey to Berkeley Lab as well as really going in depth into the process of your work. So now I'm going to continue introducing the rest of our panelists for today. We are also joined this morning by Dr. Andrew Fierro, an electrical engineering assistant professor at New Mexico Institute of Mining and Technology, also known as New Mexico Tech. I'd like to invite him to turn on his camera and share a bit about his background and research.
Hi, yes, good morning or good afternoon. I'm in Mountain Standard Time. So thank you for having me. It is a good honor to be here alongside Jared and Reva. And yeah, I want to give a quick introduction about what I do and who I am. So I'll go ahead and share this presentation, hopefully. And is that alive? Okay, thank you. All right, so Um, that was a great introduction by Reva, so I want to thank her for covering a lot of those details there about microelectronics. And what I'll talk about is a little bit more about my journey, and then um, a little bit more on the experimental side so a little bit different angle from how we can look at plasmas and how it's related to microelectronics. So a little bit of background about myself and how I became a professor in the EE department at New Mexico Tech. Really, I love computers growing up. I grew up in the 90s, and this is when computers were becoming household things. So you can actually buy them quite expensive at the time and actually take one home with you and use them at home. So I loved them growing up. I took 3 years of computer science in high school, so I did a lot of programming. Because of that, I'm from Texas, and so I was very close to Texas Tech University, and actually it was my passion to want to go there. So I was fortunate enough to be accepted, and I majored in computer science, and I graduated in an undergrad in 2009. I wanted to do a little more hands-on things. Computer science is great. You learn a lot of theory, you learn a lot of programming, but I want to be a little more hands-on. So I switched over to what my advisor called the dark side of the electrical engineering from Texas Tech, and I got my master's and PhD in 2011 and 2015. And the group I worked with was at the Center of Pulse Power and Power Electronics, but really I worked in the plasma field. After that, I was a postdoctoral appointee at Sandia National Laboratory, which is another national lab similar to Lawrence Berkeley. I worked there until 2019, and then I decided that I wanted to try academia because I really do enjoy interacting with students and teaching and doing fundamental research type of thing. So after 2019, I switched over to academia and I went to the University of New Mexico for 5 years, and now I'm an assistant professor in the electrical engineering department at New Mexico Tech. And we're in Socorro, New Mexico, which is about an hour south of Albuquerque, if you know where that is. We're a very small school, about 1,800 students in all. The electrical engineering department has about 8 faculty, and we probably have about 200 undergrads or maybe 150 undergrads and 20 or 30 graduate students. I run the low temperature plasma research group. Um, I work with currently, this is an older photo, but this is 4 graduate students and 3 undergraduate students. We're a multidisciplinary team, and I think that's an important thing that you should take away from a lot of this is that we work with engineers, mathematicians, and physicists. It's not just all electrical engineers, or it's not all just mechanical engineers. We have to work with a lot of different people to tackle this problem of microelectronics processing. And at my group, we have an opportunity to research in both computational and experimental methods. And one exciting thing about that is you get to share your research. One of those things is presentations at conferences. So often you get to travel to fun places. So hopefully in the fall, I'll be going to South Korea to present some research that I'm doing with a student and, share that publicly. And then, of course, you can publish your paper, which is sharing your work globally, where anyone can potentially read what you're doing and critique it at some point. So that's kind of what I'm up to these days. And I think I'll switch over to a little more technical about how we actually tackle this problem, microelectronics. So I'm just going to kind of give an overview of what I do, and a lot of it is in computational plasma physics. As Reva was mentioning, I work on a project with her, and I'll just introduce the concept of scientific computing and just a few key points here that at the top bullet point here is that engineering and physics codes are no longer written by subject matter experts with basic programming knowledge. And this goes back to the working with people in different disciplines, knowing people in mathematics, computer science, and engineering and physics. And where these regions overlap when we're talking about scientific computing is a region where you can develop computational models that are numerical models of real world phenomena. So in this case, we're talking about plasmas that fabricate microelectronics, but how do we simulate that on a computer? And it requires the intersection of these different fields to produce physics-based, fast models that can solve really detailed problems. Okay, and so that's kind of the project I'm working on the Reva, and she touched on with her virtual fabrication lab. Um, so the goal of scientific computing applied to real problems is we want to develop sophisticated models, so things that include lots of physics, that can help design and interpret future plasma systems because building something is very expensive. Is there a way we can prototype it computationally before we actually go and start cutting metal, as we would say? But along with this scientific computing and these models, we need experimental data to validate is what we call, and that means building trust in our computational models. So it turns out, and as you get in this field, if you decide to work in computational physics or computational anything, computers can tell you a lot of answers. And so validation is the idea of comparing our simulation results with our numerical modeling results to build confidence that our numerical model is doing something correct. When we simulate a plasma or we say that it's going to produce this type of feature in a microelectronic, how confident are we in that answer? And so validation is a way that we try to say that we are on the correct path. And so what I'm going to specifically talk about is more of this experimental data side. So specifically one area I want to introduce obviously is low temperature plasmas, which are used in these microelectronics. So, and what that means is that the plasma, and I'll just say this third or fourth bullet point, is quote unquote safe to touch. Okay, so theoretically, I wouldn't recommend this, but if you run a low temperature plasma, you apply some voltage and you create a plasma. If you were to touch it, it should not burn you. Okay, and so there's many examples of low temperature plasmas out there, and these are what are used. These are the bread and butter in semiconductor manufacturing, lighting, sterilization, and even light sources for specific things, for maybe lithography. And so low temperatures means the plasma basically stays at room temperature at 70 degrees Fahrenheit or something like that. But an example of just the opposite extreme of a not low temperature plasma, something that we don't look at in microelectronics, is a fusion plasma. So this bottom right picture here is a picture of a tokamak. If you've heard of ITER, it's how we want to generate electricity potentially in the future. And this is a case where the plasma operates at 100 million times the temperature of a low temperature plasma. Okay. And so in this case, it's a much different regime of plasmas that are applied for different applications. But for microelectronics, we're really looking at this low temperature plasma. And so what I want to talk about a little bit is just light emission from plasmas. So in all these examples you see on the top right and even the bottom right here, we can take pictures of these plasmas. If you operate a plasma, it glows in some color. And so that means it's emitting some amount of light. And that light that it emits can be things we can see, such as visible light, red, blue, green, whatever, everything we see in that photograph, but also emits things we can't see, things like X-rays, things like infrared light, out of our visible range. And the important thing about light emission is that it can influence what happens to an operating plasma. So this is a classic quantum mechanics thing that was, I think, introduced by Einstein, the photoelectric effect, where you have light on a metal surface, and that metal surface can release charged particles. And those charged particles are really what drives the behavior of plasmas. So this light must be studied so that we can improve our understanding of plasma behavior. So we actually have an experiment at New Mexico Tech that can measure light emission at different angles. So we have a plasma, we have an electrode, a piece of metal basically that has a special hole cut in it, and we collect light from that plasma, and we do something with that measurement. And that's kind of what I'm just going to analyze or just briefly show on this slide here is typical analysis of light emission is analyzed using a series of lines on this left picture where we have wavelength. So the visible range that we can see with our own eyes is somewhere from 400 to 725 nanometers. Okay, and so on the x-axis here, this is from orange to red light is what we would be able to see. And it's showing basically where we see intensity lines that go up away from zero, that there's emission in that range from orange and red. And then as we move past this red part on this graph here, we move to the near infrared part. And so this is light we can no longer see, but still could have an influence on plasma. And actually, this measurement was taken from this glowing plasma you see on the bottom right here. So this is a little bit of an experimental intro to types of things we want to measure. So eventually, we would like to take this spectra and compare it against something like the virtual fabrication lab that Reva is working on. So this is another aspect of why we care about light emission from plasmas. And of course, it's also ubiquitous with all types of plasmas, so it's something we should be able to study. So that's kind of an quick introduction to some of the work I've been doing from the experimental side, and I look forward to answering any questions you may have during the Q&A after our panel introductions.
Thank you so much, Andy, for telling us more about the process of experimentation. And we really do look forward to hearing more from you during our question and answer segment of the program. But we are now going to be moving on to our final panelist for today, Dr. Jared Ashcroft, who is a chemistry professor over at Pasadena City College and the Center Director for the Micro Nanotechnology Education Center.
All right, thanks everyone. I'll make this quick so we can get to questions. So I'm Jared. I teach chemistry at Pasadena City College, also the PI of the Micro Nanotech Education Center. Think of microelectronics as like a water hose, right? Whenever you turn on the hose, water's going to come out. What my job is finding students who can help make the devices that do exactly the same thing with water to electrons. Right? Like these computer chips or microelectronics that we have, you basically have some electrons sync, and we're going to make devices with transistors or resistors or semiconductors or whatever. And all of these little devices, when turned on and off, are going to control the flow of those electrons in your electronics and basically gives us energy. So really what I want to present right now is what are some alternative workforce pathways? Like if you want to be a person who just wants to fix instruments like machines or equipment that we use to make these machines. If you want to work in a clean room and like being actually like developing or like creating the semiconductors, we can do all of that. And again, it's all back to this electron and moving it around and basically just controlling how that movement is to give us energy. I want to just share a program that I have with you. It's called the Advanced Technology Technician Training Program. The goal of this is to make students like you aware of what the microelectronics industry is, what semiconductor companies are out there. There's a company called Texas Instruments. It's TI. Everyone thinks it's a calculator company. It's actually 95% of their work is making semiconductors. The calculators are about 1% of their work. So like what we do is try to bring industry professionals to meet with you. We give you sort of an online presence where we'll bring Micron and Intel and TI and Synopsys and ARM and all these companies and their recruiters to just show you this is what you would do in microelectronics or the semiconductor field. At the same time, we try to give you access to training like VR training or credentials like the CTECS Workforce Readiness credentials, semi-foundation credentials, so that you can get outcomes that can help like build your resumes to get you the jobs or get into like internships. We have a lot of mentoring. So we have student mentors, industry mentors, faculty mentoring. Like that's a big component of it. We'll work with you on helping you develop resumes. We'll work with you for interviews, like do mock interviews and stuff like that. But the big component, make sure we provide you mentors. It's not just me, I'm old. We get you young student mentors that are really like right now looking for jobs or have been in our program before, so that like you just get a sort of an experience that's more with someone going through the same process that you are simultaneously. Focus on student outcomes. Like I'm a person who believes if we give an internship program, the learning component is great, you know, learning critical thinking skills, learning all those soft skills. But what I really want to do is make sure that you're going to have opportunities on the back end to apply for internships, to write papers, to present. We've had over 50 students published. We've had about over 100 presentations. Like every year, we try to get students opportunities to build that resume, help you apply for like Goldwater scholarships, help you apply for Jack Kent Cook scholarships. It's basically like, how can I help you get the outcomes that's going to lead to you giving a better chance to get internships and jobs. We have our own peer-reviewed journal. Like we created this journal specifically for students and community college faculty so that they could write papers and have them peer-reviewed and get a paper on their resume pretty easily. So if you're interested in writing papers, it's great to join our program. Or even if you're in a program right now, like just submit a paper to JATE. And our goal is to help you through the writing process and the submission process and review process. So at the end, you get a publication. AT3, what is it? So it's 8-month community college internship program. We also take high school students and university students starting now. The goal is to try to get you into technician jobs. About 75% of our students go into technician jobs, 25% into engineering internships or transfer. Every week we'll bring industry, university partners, and I got great university. If you want to meet Caltech or MIT or Princeton or Cornell, they're all partners with me and they'll come and present internships to you. We have different stipend levels. So like the Tier 1 students, which is more technicians, they get $1,000, access to VR simulations, internship application and internship placement help. For high school students and engineering based students, the only difference is really it's a $250 stipend. The only reason there's a difference is the grant that funds it. It's for technician training. So I have to give those technician students a higher stipend to make NSF want to fund me. But then really the important part is facilitating entrance into those summer internships. We have someone at Micron, about 5 people at Micron this year, and they're all getting $30,000 to work at Micron for 4 months. We also place students in this summer internships at universities. We placed 125 students in internships this summer. And right now the program is open. Like you just have to email me and basically I add whoever emails. No one gets rejected from our program. Everyone who applies gets in. And then at the end, we'll get you some certifications, job interviews, industry internship interviews. I wanted to kind of end with some advice. You know, like, because a lot of times you don't know, you're applying to internships and what happens. 1, apply to everything that you can. If you don't apply, the answer is always no. 2, whenever you get rejected, you're allowed to be really sad and really mad for 24 hours. Like I know when I write grants and I get that rejection letter, I can't tell you here what I actually tell the mirror to myself, but it's not really nice. Rejections happen. That's part of the process, and you're allowed to be disappointed and sad. Just don't let it linger for more than 24 hours. When you get acceptances, the same thing. Be happy, celebrate. You get 24 hours to look in the mirror and tell yourself that you're the greatest person in the history of the world. That is completely fair. And then after that 24 hours, like ask yourself, all right, what do I do now to make this internship like awesome or job experience awesome? Undergrads, high school students, you don't get to choose your research project. Take any internship you can get. My first internship that I actually left Long Beach State was at the Kansas University Medical Center in a toxicology lab. The first day they gave me 30 baby rice and told me to sacrifice them. And I am not kidding. It was like, let's mess with the intern day and make him in tears with all these baby mice that I was forced to, take care of. It's why I do not do animal research, because I did that internship and I realized there's no way in my life that I could do that forever. It was still a great experience, and that's another reason to do these internships, to realize what do you not want to do just as much as what you want to do. Be willing to move, right? Get out of your comfort zone. Like some internships, they could be in New Mexico. I mean, I send about 20 students to the University of New Mexico every single year. I'll tell you, Intel is trying to hire 30 people right now as maintenance technicians in Albuquerque. So if you're willing to move, a lot of times your network can grow and you have more opportunities. Check your emails every day. Don't have 3,000 unread emails. My son, he's just going to college. During the process, he applied to MIT. They sent him an email 2 days later for a job, for an interview, and he didn't check it for a month, and he missed the MIT interview. Learn to check your emails every day, and don't have a bunch of them there, because you're going to miss something. And then sometimes, I hate saying this, sometimes you need to take internships as a volunteer. It sucks, but not everyone has funding to pay for you. And sometimes that first, non-paid internship can lead to the better internships in the future. And with that, if you want to email me, again, we have openings in AT3 right now. We had our first meeting today. If you're interested, just send an email to my pasadena.edu. And this is like an NSF funded center that I wanted to share. And I hope I did that really fast, because I know we got to get to questions.
Thank you, Jared, for sharing all the super cool opportunities that your program offers. And also just thank you to all of our panelists in general for giving us some more background information on you guys and also the context of today's conversation. But I'd like to invite all of our panelists to turn on their cameras, as we'll now be moving on to the Q&A section of this program. And I'd also like to encourage people in the audience to put questions into the chat box while we start with some that we've created. So this is a question for everyone. Microelectronics have many real-world applications. So what projects have you guys worked on or seen that have had the most real-world impact? We can start with Jared, Andy, and then Reba.
Yeah, I mean, so I think for me, the real world impact right now is, I mean, I don't know if everyone's aware of the Chips and Science Act and the need for bringing chip design and semiconductor manufacturing back to the United States. Currently, 95% of these very complex chips that are needed in every single electronics device are made overseas. And the reality is, if we don't onboard or bring that manufacturing back to the United States, then we're going to be at a disadvantage globally in just like having access to these high-end chips. So I think a really real world application is just the development and actually just the fabrication of these very high complex technology, and we need to bring it back to the US to at least at some point.
Yeah, I think from my perspective as a professor, I think the application for me is teaching. We have these grants to do this type of plasma research, which is involved in this microelectronics processing. And the real world project for me is training the engineers and scientists and physicists of the future who will hopefully contribute to that goal of having domestic microelectronics fabrication, so that way we can hopefully produce stuff here in the United States. And I want to be a part of that, as far as being able to train these students who are undergraduates or graduates who go off and do great things and are contributing to the production we do domestically.
And yeah, and adding to all of that, the real world application that I look at is bringing a partnership between the national labs, like Berkeley Lab, where I am, and the private sector, the industry. So we talk to people in the industry, try to understand their needs, and then develop computational methods to support the objectives that they have in mind when it comes to fabrication of microelectronics devices.
Yes, totally. I think it's super interesting to hear about all the different ways microelectronics has so many real-world applications. And moving forward on our next question, mostly focused on Riva and Andy, plasma is a prevalent matter in this field. Can you tell us a little more about plasma's importance in regards to microelectronics, and what specific role does plasma play in your work? For this question, I think we'll start with Riva and then Andy.
Thanks, Dominic. I read this somewhere and it's actually true. Every semiconductor chip that you see has been touched by plasma. And that's the importance of plasma when it comes to microelectronics and semiconductors. What I mean by that is, if you recall the slide that I had shown about the fabrication process, the patterning process involves lasers, which is high energy, which is kind of plasma anyway. And then you have plasma that's used for etching these semiconductor chips. And so there's plasma involved there too. Now, I've said the word plasma so many times, I just want to back up and reintroduce what plasma is. It's basically highly ionized gas where you have some sort of a collective behavior of these positively and negatively charged particles.
Reva, I think you're correct in that article that every semiconductor, it might be like plasma is involved in 50% of all processing parts of it, whether it be producing the light or the charged particles themselves. And for myself and my students, we use plasma every day. We make it every day. We're simulating something every day, and it is a critical issue in microelectronics fabrication. And there's so many details in the plasma. Of course, it's hard to get into them here, but there's so many fine details that can be looked at to improve the plasma, to make some process more efficient, because um, we want to get better. We want to make smaller things. We want to make bigger devices using smaller things. And to do that, we have to focus on what is the plasma doing that is doing the process. So we might have to control the direction of something or the exact wavelength of something. And so plasma it is a critical to processing things in microelectronics. So I think understanding it is critical to moving forward in the future.
Yes, I think it's crazy to think how much we are exposed to plasma without even realizing exactly what it is or what it does. But on to the next question. With the quick pace in which technology is constantly changing, where do you guys see the biggest opportunity for innovation within the next 5 to 10 years? And we can start with Jared, then Andy, and Reba.
I actually think this is a really good place to talk about Helen's question too, about recommending students hands-on part of the field. The reality right now, like in the semiconductor industry, because of ChatGPT, because of AI, because of all this artificial intelligence that's happening, a lot of those engineering jobs that you all, especially computer science, that are right now sort of filled, they're going to change completely and go away. Computer science, all these AI things can do it a lot better than us. And so there's going to be a big transition that's going to happen from the need for engineers to a bigger need for technicians. Like, I promise you, in 10 years, what you're going to see is people with engineering degrees versus technicians, they're going to get paid the exact same amount. Because if you can't have people that can actually fix those instruments, and that, like Intel right now, if one of their instruments goes down, it costs them over $100,000 every minute. Right. So if you can't fix that instrument and Intel's losing $100,000 every minute, they're going to be in bad shape. So I think that what Helen says, like getting into even a community college program where it's maybe a side thing and doing an advanced manufacturing, electronics technology, semiconductor program some people have. If you can get that and you actually get some hands-on experience on how do you actually make these things, how can you fix the equipment, you're going to be at an advantage if you then go on to an engineering program that their education is going to be flipped on its head over the next 10 years because of AI. So I'm a big proponent. I think using hands-on learning and getting, how to fix things and how to creatively think through problems is going to be a lot more important than that technical skill that you might need in just designing or doing process flow. So I think AI is going to be a big game changer, at least in the industry over the next, 5 to 10 years. Now with university and research labs, which the other two panelists are talking about, that's different. But if you're looking for industry jobs, get into a lab and get hands-on experience as soon as you can.
That's great advice. I think from the technical side, the research side, at least for us, a big thing that's coming up is what we call high aspect ratio in etching. So this is for building 3D devices, for instance. So normally semiconductors we build in a 2D plane. But now, what if we want to build a hard drive that goes vertical as well as horizontal? And so this introduces its own set of challenges to be able to drill a hole essentially down through this thick vertical device, which is an area of research that's ongoing right now. How do we do that? And the reason is we can make memory more dense, we can make hard drives more dense and smaller, and so our processors potentially having in the same footprint having more computational capability. So these are why we'd want to do something like this. So I think that is one area of research, open research right now that is being worked on. And I think Samsung has already started producing some 3D devices, 3D DRAM devices. So that is something that is coming up on the forefront.
That's perfect, Andy. Yes, I also wanted to mention about high aspect ratio etching, but since you've already mentioned that, I want to give this another angle of research, which is we have these traditionally made integrated chips, and we are sort of moving on to 3D. But then there's, as I'd shown in my second part, that there are two ways. One is manufacturing, and the other one is innovating something that's completely new, like thinking about materials in a different way so that their properties can be used in future microelectronics devices. This is an absolutely new field, and we don't know what to expect. So there's a lot of research ongoing on this topic. Like the things that you can think about is spintronic devices or quantum computing devices and so on. So those are the other aspects of what to expect. It's not that it's going to be ready for us to use in the next 5-10 years, but at least we'll get closer to understanding them.
Yes, so as innovation skyrockets, these tech industries are rapidly changing, and because of that, sustainability is becoming increasingly important in all areas of technology, especially AI. I want to ask you all about how the microelectronics field addresses energy efficiency or environmental concerns, and what role does your work play in supporting more sustainable solutions? For this question, again, we'll go in reverse order, so we'll start with Andy, Riva, and then Jared.
Yeah, I mean, a sustainable solution is something that we're all striving for in a lot of different areas, and it's no different in microelectronics. I think we want to make processes more efficient. So can we do things better? We make our yields higher. So we submit proposals. I submitted one last year to try to improve the energy efficiency of nitrogen cracking. So if we can do that and make radicals that at a cheaper cost, that saves us some some electricity, hopefully, over the grand scheme of things when you're producing thousands of microchips. So it's a tough problem. I think you see it with AMD or you see it with Intel that one of the big things they want to do is lower power consumption. I think some of these factories for something like AI, where our power budget or a lot of our power budget is going to go to training data or storage facilities, which all rely on um, these processors that could be more energy efficient than they are currently. So, not only from the manufacturing side being more efficient, but also from the implementation side on the industry side, we'd want to be more efficient.
Yeah, and the other aspect, again, adding to what Andy had mentioned, is that, with the use of AI and IoT things, the need for all of these transistor semiconductor chips is also increasing. So we need to manufacture more. And that manufacturing process has to be energy efficient. A lot of times, engineers, they sort of know what their recipe is for, which knobs to turn to run that device in order to fabricate the microelectronics chips. But with the process becoming more and more complex and the chip becoming really, really small, and also the 3D high aspect ratio design that Andy had mentioned, it's really hard to ensure that you manufacture ultra high precision chips. And so what we do is basically try and help out to understand what is that optimum parameter space to have when you are running the device, so that you get the most high precision and high yield. And that's how we try to improve the energy efficiency of the manufacturing process.
I guess I look at everything through like a workforce problem, because that's kind of like my space versus the research problem. And as we're making these things more complex, which is what's going to happen if we want them more efficient, like I think one thing that we ignore is, how do you train the workforce that's going to actually make them? Right? Because you can do all the R&D that you want, you can make these really efficient processes, but if we don't have at least some focus on, well, here's the people who are actually going to be making these devices, and they need to understand sort of like why we're building something that's more efficient, then it doesn't matter what the R&D does, right? Like if there's no way for industry to take that, because the universities is where all of these advancements happen. If the companies can't take those advancements and then put them in their manufacturing process and have their workers be able to do those processes over and over and over, then I think that we're always going to be trying to like innovate, but never actually implement. Right. I think that there needs to be a little bit more focus on how do we train our workforce and train the students who are going to actually be making these devices, so that they understand how whatever the complexities of this environmental aspect and sustainability is. Otherwise, we're just going to keep having the same exact, Intel's going to make their fab, or TSMC is going to make their fab, and they're going to be the same type of fabs. So that's what I think. I think we got to think of workforce simultaneously as we think of the R&D.
Okay, I know we didn't get to exactly share out a bunch of the questions from the chat, but I've seen you guys have put in some answers yourselves. But we are going to move on to the last question of the session. So, in 1 minute or less, what do you wish you had known in high school or early college that would have made your career path a bit easier? We can go in any order.
I mean, if it was me, I'm a natural introvert. I don't talk to people. Like I'm very, and I wish that what I would have known in high school and through college is more communication skills, more chances to present, more chances to be in groups and actually speaking up. I think developing your communication skills is by far the most important thing that you can do. Written communication, oral communication, and just how to work as a team. We can teach all the technical skills. All the technical stuff is easy to teach. You can all learn it, but learning how to communicate and how to advocate for yourself through that communication is the best thing you can do for yourself.
think one thing would be uh, when I was writing my thesis, I spent 6 months writing it in advance, and I got to the day of my defense, which is 2 or 3 months before graduation, and I remember being in the lab, and my advisors, I was 30 minutes to defend, and my advisor says, "Don't you have a defense in 30 minutes?" And I was pretty relaxed, and I just thought to myself, yeah, I started a long time ago. I'm done with everything, and there's nothing really to stress about. So, I learned, I figured that out in grad school. So I wish I would have known, and everyone knows this, the procrastination, like getting started early on things, taking care of things earlier, just so, um, it's a little less stress in your life that you don't have to have. So rather than doing something that wait a week on, start that week that a week or two before, and you'll be surprised at how much you can get done and how much better of a job you can do and everything like that. So of course everyone knows that, but a real world example from me was my thesis defense, and it went smooth, and obviously I passed, so that was good.
Agreed with both Jared and Andy. Communication and also trying not to procrastinate. And along those lines, I think the other thing that I wanted to add, I wish I knew it when I was in high school, is that perfection is the enemy of, trying to get things done. Sometimes you don't have to be perfect. For example, let me say, when I try to write something, before I used to write and then do backspace and then write again and then do backspace. But now I tell myself, this is my first draft. I don't have to be perfect. I'm going to put my ideas in there. And then I can go and repeat over. So that's another thing to add perfection. And also, I don't know whether you've heard the term imposter syndrome, but that can be real. And everybody goes through it. Everybody, right from, anybody that you meet in science will have a moment in their life. You can ask anyone on this panel too. Will have a moment where you feel like, oh, I don't think I know everything about this, but you don't need to. You work on it anyway, get started with it anyway, and then you will learn in the process.
Yeah, thank you guys all for the advice, and thank you so much, Jared, Riva, and Andrew, for answering all of our questions. I'm going to hand it over to Molly now, who's going to finish us up for today's career talk.
Thank you so much to our panelists for sharing more about the complex world of microelectronics. I would also like to thank our two moderators for today, Kyla and Dominique. And lastly, thank you to our audience members for staying engaged. Just a reminder to check out our past career talks on our website. And our last STEM career talk of this summer will take place next Friday, July 18th, where we will be focusing on geothermal sciences. Thank you and have a great rest of your day.